Okay, so quick enough video hopefully on graphs of the derived function. So what we mean by the derived function is the function of the derivative of a function. So the derived function is the function f dash x for a function f of x, so the derivative. And we can use the relationship between a function and its derivative to kind of describe what the graph of the derivative would look like. So the things that we know kind of listed here, like if the function's increasing, then the derivative is greater than 0. If the function's decreasing, the derivative is less than 0. When the function's at a turning point, our derivative is equal to 0. So we're using those and now tying those to how the derivative function would act. So if the original function is increasing, my derivative function or my derived function should be positive above the y-axis. If it's equal to 0, if I'm at a turning point, then my derived function would be crossing the x-axis at that point because that would be a root of the derived function, and so on and so forth. So being able to kind of connect those different points and those different values is kind of really important here. So the derived function is the function f dash x. If we're looking at an example here, use the graph of f of x to write down the range of values for which the derived function is equal to 0, the derived function is greater than 0, and the derived function is less than 0. So on the right hand side here, what we have is the graph of the original function, f of x. So this is the graph of f of x. And they want us to kind of use that now to talk about the derived function. So I should know that when my derivative is equal to 0, that's at a turning point of the function. So that's going to be, say, for this value here, and also for this value down here. So what that means here is that f dash x is equal to 0 at what x values? Well, it's equal to 0 at x equals to minus 2 and x equals to 1. So x equals to minus 2 and x equals to 1. Those are the values where my derived function has its roots, or has its turning points, okay? So those are going to be the two values there. Then looking at the range of values for which the derived function is greater than 0, well, that's where the original function is increasing, So that's going to be for this blue part here up to minus 2, and for this part here after 1. So when x is less than minus 2 and when x is greater than 1, that's when the derived function will be positive. Okay, here we're asking then where's the derived function negative, and that's going to be between those two values. So greater than minus 2 but less than 1, between the two values. Then they've asked us to sketch a graph of the derived function, so we can sketch a quick little graph, noting as well that this is a cubic. So I'm expecting the derived function then will be a quadratic. Okay, my derived function will be a quadratic function then. So I know that my derived function is going to have roots at minus 2 and 1. Before minus 2, it's going to be positive, and after 1, it's going to be positive. It's going to be negative between those two values of minus 2 and 1. So if I'm just sketching it out here, minus 1, minus 2, 1, 2, 3. So let's use the two roots. I know it crosses or has roots at minus 2 and 1. And I know that it is positive before minus 2, it's negative after, and then terribly drawn. And then it's positive again after. So that's a general, and again, sketch. It is not a work of art. It is a sketch with the information that they have given us at this point and the information they've asked us to look for. So that's kind of the key thing there for us, is just kind of using what's available to us and using the information that we have, making sure that we know kind of what all of it means. So let's jump into another example. We're matching each of the following functions with the graph of its derivative. So looking at the functions that I have, I start with a cubic. So the cubic is probably going to match up then with the quadratic function here, okay, and so on and so forth. So let's start by looking at I suppose, by looking at the derivative ones here underneath, and we'll try and match them back up with which function are they the derivative of. So a is a line. So a line, if this is the derivative, it probably started as a quadratic function. So that would probably mean then that a must be the derivative of g. It's a line. We can also see that the line has a root at 2 here, and that is the turning point of my quadratic function. Okay, so that lines up with everything there. Looking at the next part here, I have a nice horizontal line, and that to me says it must be the derivative of a linear function. because if we look at my linear function has a slope, has a rise of 3 and a run of 1. So it has a slope of 3 over 1, or just 3. And this function here is just the function 3. So remember, if I differentiate h dash x, that should give me the slope of the line, which is 3. And here we are equal to 3. Okay, so matching it up that way. And that, of course, means then that c must be the derivative of f. And again, as we expect, we go from a cubic. If we differentiate, we get a quadratic, and looking at kind of the roots and where it crosses there and all of those relevant pieces of information then. So let's jump into an exam question or two, I suppose, then on that. So the exam question says the graph of a cubic function px is shown in the first diagram below. The maximum value of the derivative in this domain is 1. So what that tells me here is that the highest point I'm going to be reaching is the point y is equal to 1 here. That's a y value. I don't know what the x value that goes with it is, but I know the highest y value I'll get to will be 1. And the derivative at 0 is equal to minus 3. So I need to use this information to draw the graph of the derivative on the set of axes below. So first of all, I know that when the derivative is 0, the value is minus 3. So let's just plot that point in here. So that's coming from this piece of information here. The other things that I know, or that I can look at, are the turning points of my graph. So my graph has turning points at the two x values of 3 and 1. So I expect those to be then the roots of my derivative function. Okay, so the roots of my derived function should be the turning points of the original function. And so the last little points I have, I suppose, are the 4 and the 2. Okay, so the 4 and the 2 really are the only points that I don't have information for as of yet. Okay, they're the only points that I don't have full information for. So I could work out the exact value or the exact function of my derived function. So I know that this function here has roots of 1 and 3, so it has factors minus 1 and minus 3. I'm putting in the a there as kind of my integer factor. So I know that at x equals 0, y equals minus 3. So let's sub that in. So a 0 minus 1, 0 minus 3 equals minus 3. So a times minus 1 minus 3 equals minus 3. 3a equals minus 3, so a is minus 1 there. So a is minus 1. So I can work out this whole function here. Then if I multiply out those brackets, I get x squared minus 3x minus 1x plus 3, and all multiplied by minus 1. So I get minus x squared plus 4x minus 3. So I can use that now to find when x equals 2 to find out what the value is. So minus 2 squared plus 4 times 2 minus 3. So that gives me 4 plus 8 minus 3. Okay, I think something's gone amiss there. That'll be minus 4. Minus 4. Okay, and that's going to give me a value of 1. So when x is 2, my highest y value would be 1 there. And then evaluating for 4. So let's do minus 4 squared plus 4 times 4 minus 3. So that's minus 16 plus 16 minus 3. So at 4, I'm back down here at minus 3 again. So I've worked out all the information that I can about this graph, so I can draw a nice little graph of the function. Noting here, there is a slight difference here because they're asked to draw the graph, not just sketch, but to actually kind of draw a somewhat accurate graph, I suppose. So using all the information we have, we're pulling ideas there now from your Algebra 2, from finding the roots of the equation, finding the factors, using that to kind of construct the equation itself. We also could have used there maybe the constructing the quadratic from its roots, but I suppose when we're finding factors, then we have to always, when we're finding specific functions, we have to use that idea of the integer factor as well to help us find the exact function that we have in the question. Let's just look at one more exam question. Here we're given a set of graphs and we have to identify the graphs which represents each type of function, and then which is the first derivative of that function and which is the second derivative. So first of all, let's look at each function. So I can see there f is a cubic function, so let me put that down. I can see that g strikes me as being a trigonometric function. H seems to be exponential, and k then would be my quadratic function. So looking now, comparing the top row with the next row, and I want to say which is the derivative of each one, well, I can see if I skip over a there, I can see that b is a line, and I expect a quadratic function to go down to a linear function. So if I look at my quadratic function, its first derivative must be the line there. Then looking at the next one that I can do, I see d there is a quadratic function, which must have come from a cubic function. So I'm expecting d to be the next one there. If I look at a is a trigonometric function. It's actually a cosine graph, and I'm presuming then that comes from the sine graph that I had at the top there, and then that would leave then c as the derivative of my exponential function. Now comparing the first and the second derivatives, I expected b there, a linear function, to then just go to a y is equal to situation. So b then must go to 1 there. The next part of the linear function I have must have come from d, so that would be 2. The trigonometric function again should stay as a trigonometric function. So remember, our trigonometric functions go say sine to cosine to sine. They kind of repeat that way. And then I expect the last one to be the derivative of my exponential function there. Okay. So for one row, we have to explain our choice. So we could say the quadratic would go to a linear. So a quadratic will go to a linear function. So that's why k goes to b. And linear gives a constant when it's differentiated. So when I differentiate a linear function, that will go to a constant function. Okay. Similarly, we could explain the other ones. A cubic function would go to a quadratic, which would go to a linear. Okay, the degree of the functions is decreasing there. The trigonometric functions, we could say, well, trigonometric functions stay as trigonometric functions, just kind of alternating. So it starts with a sine function, and then it went to a cosine function, and then it's gone to a negative sine function. Similarly, exponential, and kind of the way that the exponential function is moving there. So just some sort of explanation is all that's required there. But you can see again with these functions, graphs of derivatives, you need to really understand what's happening with the derivative and being able to really explain what it means for the derivative to have certain characteristics and be able to match up, well, the turning point on one function will give me a root of my derivative function. Where my original function is increasing, that's where the derived function would be positive or greater than 0. And being able to use that information not just to kind of find where the original function is increasing, but also to kind of describe the derived function or draw the derived function or answer questions on the derived function. And particularly those questions as well where we have to kind of match the function to the graph of its derivative, being able to kind of do that somewhat fluently. I suppose being able to talk about or describe what the graph of the derivative is doing is really key and kind of shows a deeper understanding of what's happening. And we see that kind of in later questions here as well with the rates of change and things like that, that it's important to understand what the derivative means in context and how the derivative changing impacts the original function or kind of stems from the original function.